Hello everyone. I'm Toshi Hirabayashi from Georgia Tech. Today I am going to discuss a little bit about different story of hematite distribution, particularly from geological processes. I'm not a geochemist. I'm not going to discuss any geochemistry, but I'm going to discuss a little bit about geology. Is that mic is on? Not working. Not working. How does it work? Maybe just flip on the screen then. Okay, try again. Oh, that works. All right. Shuai Li et al. Recently published blockbuster paper discussing the distribution potential existence of hematite. Preferred interpretation of finding is that Earth winds potentially affected lunar surfaces to form hematite over the recent amount of time. So estimates of formation of hematite was that to have the current distribution of hematite, a 15 nanometer thick layer should be exposed over 100 million years. However, if we look at a geological aspect, we have a different story. So if we look at this plot, this is showing the distribution of hematite on top of the distribution of slope. If I combine those two, we'll be able to see the histogram. So this is showing the data sample of hematite as a function of slope angle. If you look at this histogram, basically 10 degrees to 25 degrees, that would be the major distribution of hematite. However, if we consider a geological process, this is not negligible to have mass wasting or disturbance. So I am going to discuss two different geological processes, particularly looking at impact-induced processes. First one is impact mixing. Impact mixing is basically having the disturbance, particularly along vertical direction, by considering a numerous number of cratering processes. On the other hand, topographic diffusion, this is a topographic erosion driven by impact emplacement. And then what happened would be mass would move over lateral direction. People have been working on those problems, and we have a decent number of modeling, and we're gonna use those two models. This is a very simple schematic, but in terms of impact mixing, first, I am going to look at impact flux, impact cratering geometries, and a depth. Those are input, and output we call area fraction of disturbed area at a given depth. I'm going to discuss that later. In terms of topographic diffusion, we can use three-dimensional diffusion equation to characterize elevation change. So from now on, I am going to discuss topographic diffusion effect first. In order to characterize topographic diffusion, we need to determine first, we call diffusivity or kappa. This number is basically determining how fast diffusion occurs. If you have higher diffusivity, then diffusion is going to be faster. If you have lower diffusivity or kappa, you should be able to get lower diffusion. I am showing here kappa of 2 square meters per million years. This is almost equivalent to the diffusion level of sub-kilometer scale topography. The left plot is showing elevation change map over the entire lunar surface, particularly looking at the South Pole. And the green dots are showing the distribution of the hematite. If I combine those two data, we can see the histogram. So histogram showing the elevation change at a given hematite distribution. If you look at this value, basically elevation change is mostly between 10 to the minus 4 and 10 to the minus 1 meters. Technically, if you pick 99% level, this is 100 micron. So if you remember, I said 15 micron thick layer. This is technically disturbed by topographic diffusion. I am showing here a different case. Kappa is 700 square meters per million years. This is technically showing tens of kilometer scale topography. I'm believing that this is actual reasonable value. The reason is major part of hematite distribution is on the wall of large craters, like tens of kilometer scale craters. If you look at this, then the distribution of elevation change is actually higher than 1 millimeter. So 100% of the location having hematite should have elevation change higher than 1 millimeter over 100 million years. This is 2 orders of magnitude higher than 15 micron thick layer. I'm going to switch to mixing depth. So mixing depth here, I am only considering primary craters with a size up to 1 kilometer diameter. And we're not going to discuss a secondary cratering. This is because I wanted to show a lower case. In terms of this graph, this is the area fraction as a function of depth. I'm going to discuss how to read this plot. Let's look at those 2 lines. Blue is showing ejecta blanketing only. If you look at orange, this is the breccia lensing and ejecta blanketing. When you consider impact mixing, breccia lensing is the dominant contributor to disturbing the surface. When you look at ejecta blanketing only, you'd be able to see at 1 centimeter depth, area fraction is 99.9%. By this, I mean over 100 million years, ejecta only can completely disturb the depth up to 1 centimeter. If you consider 10 centimeters, then area fraction is 0.4, meaning that 40% of area would be affected by ejecta blanketing over 100 million years. So using this finding, we would be able to see that over 100 million years, you would be able to see 99.9% of area would be completely disturbed by impact mixing. This is the 3 orders of magnitude higher than 15 micron thick layer. So I'd like to bring this as a take-home message. So if you consider geological processes, basically we have a completely different story. 99.9% of area would be completely disturbed by any geological processes, particularly considering impact mixing process. Topographic diffusion, impact mixing, those can give different level of impact mixing. However, depending on looking at which process, the level would be orders of magnitude different. We are currently trying to get interpretation of this discrepancy between geological aspect and chemical aspect. And I'm hoping to be able to give some insight in the future. With that, I stop and I'll take questions. Thank you.